Hello and welcome. The purpose of this video is to walk through the IA analysis practice sample data. So that's using that research question, what is the effective temperature and the concentration of HCl? Various 25 cubic centimeter aliquots of HCl were titrated against NaOH. And here's the information you have about NaOH. This was done with 3 trials at each of these temperatures in order to analyze if temperature affects the concentration of HCl. Okay. So the one thing to notice in this video, I'm not going to go through how we got this zero point 0.1. That would come from propagating the error of the mass and the volume of your NaOH, which you would have measured in order to get the uncertainty. Um, and so you can propagate that error. Hopefully this video will help you work through error propagation. If you do have any questions about how I got that, you can feel free to come and talk to me. Okay, so we're going to walk through the error propagation specifically around HCl. So in the raw data, we show absolutely no processing. So the first thing I needed to do was I just needed to get the actual volumes of NaOH used. I had an initial and a final volume, and I needed to subtract in order to find that volume that I added to each reaction. With a burette, you do subtract initial minus final because of how the burette markings work. So the volume is initial minus final. And even for something as simple as subtraction, I need to show the equation generally, and then I plug in specific numbers. So I use this first trial, 5 degrees Celsius, trial 1, as an example throughout my calculations here. I just chose that trial and then I kept using that as my example. So I just plugged in those numbers and I show the volume. I don't need to show the calculations for every single one of these. Just showing the equation that I use in a sample calculation is great. You'll also notice I have an uncertainty here. It's important that I show how I got this uncertainty. So a couple things going on here. This is the square root of the sum of the squares method. This is one of the methods the IB presents to you in order to find uncertainty. You may have learned in other classes to just add the absolute uncertainties. You can do that as well. The IB will also accept that method. This is the method that I showed you in your homework. So this is the method that I'm going to show you throughout this video. If you choose to just add the absolute uncertainties or add percent uncertainties, that's fine. Just make sure you're keeping things consistent. All right. So in order to use this sum of the squares business, I just take the uncertainty from each of my measurements that was involved. So these 2 volumes were involved. They both have uncertainties. I take the uncertainty of each, I square it, and then I take the sum. And then I take the square root. Well, I take the sum and then the square root. Sorry, I follow this formula. And I want to report correct sig fig, so I'm adding these values. They each have 2 decimal places. That means my answer will have 2 decimal places. You'll notice if you report this method, your error ends up being a little bit less, which is good, I guess. We want to be as accurate as possible, but this method does, of course, result in slightly lower error calculations. All right, so now I have my volumes for my 3 trials. This is not really helpful to do stoichiometry with, right? Because I still have 3 different trials. So my next step is going to be to take an average across these 3 trials. So I took an average here. I show this formula. Notice I recommend actually using the insert equation here. I don't think it's a good idea to show the formula like I did on one line. I did that because I wanted to keep everything in Google Sheets and not move back and forth, but please do keep that in mind. Use the insert equation function if you need to, um, if you need to put an equation in your IA. So again, I use example data here from that same trial 1, 5 degrees Celsius. All right, I have a whole column of uncertainties. I also need to show how I calculated those uncertainties. These are averages. We do averages in a special way. If you go back to that IA homework 4 and error propagation, this is the half of the min-max uh, strategy. And so I just take the highest value minus the lowest value divided by 2. This is a special way to propagate error if you have an average. And so, for example, in trial 1, Let's see, my highest value 2.30, my lowest 1.5. So, oops, this should be 1.5 actually. 1.5 was slightly lower than 1.55 divided by 2, and that probably changed that slightly. 2.3 minus 1.5 divided by 2 is 2.3 minus 1.5 divided by 2 is actually going to be zero point 0.8 divided by 0.40 here. Sorry about that. Okay. And then I did the same thing here. So just looking at my three values, figuring out which is highest, 2, 1.35, subtracting those and dividing by 2. Okay, notice that I'm keeping sig figs consistent. So in this case, I'm doing subtraction, so I need to match up decimal places. And so 2 decimal places, 2 decimal places. Looks good. My uncertainty, the precision of my uncertainty matches the precision of my data. That's what I'm looking for. All right, so now I have my volume of NaOH. Volume of NaOH. I did not show it here, but you would have shown it, of course, in your introduction. The formula that we're working with, NaHCl plus NaOH yields water plus NaCl yields water plus NaCl. Now that I have volume of NaOH, and concentration of NaOH, I can use that to find moles of HCl. Like in any titration, I have my volume of HCl, that was 25 cubic centimeters, so I can find my concentration here. All right, so in order to find my concentrations, I'm showing my stoichiometry here. I'm just doing the volume, converting, of course, to cubic decimeters, then using the the molarity, excuse me, of the NaOH that I had, and then of course changing that to moles of HCl. And again, show a sample calculation. And then the next step to find the concentration, moles of HCl, those moles that I just found using the stoichiometry, divided by the volume of the HCl aliquot, which you see we reported right here. The volume of each of these aliquots was 25 cubic centimeters. So pretty straightforward stoichiometry, pretty basic titration here. I get my different concentrations, which are the moles per decimeter cubed. Of course, your moles will change each time. The amount that we had that we titrated with was 25 cubic centimeters or 0.0025 cubic decimeters of HCl the entire time. Notice I'm reporting all of these decimal places because this was the precision, 25.00. I had 1, 2, 3, 4 sig figs, and so I'm maintaining those 4 sig figs even when I divide by 1,000. Division multiplication, you go by number of sig figs. So I'm being really careful to maintain that correct number of sig figs. Okay, again, my uncertainties are, or excuse me, okay, that's all I wanted to say about that. Just be careful of sig figs. All right, now the next part is to find the uncertainties for each of these values. So, whoops, I did not mean to move that. So, how do I do that? I need to take every value that had any measurement involved and find its relative uncertainty. So, the volume of NaOH, that involved a measurement. That means it has an uncertainty. Converting between decimeters cubed and centimeters cubed, there's no uncertainty there. That's just a number we look up, a conversion we look up. Here, this 1.5 moles of NaOH, this had an uncertainty because I had to measure the mass and volume of my NaOH in order to make my solution. Coefficients don't have an uncertainty, but the volume of NaOH, the concentration of NaOH, and then the volume of HCl, this was the other thing I had to measure. This also has an uncertainty. So for these three things, the three things I measured, I need to find their relative or percent uncertainties. Percent uncertainty is the absolute uncertainty divided by the measured value times 100%. All right, so to find the relative uncertainty, also known as the percent uncertainty, of the volumes of NaOH, I take the uncertainty divided by the measured value. So you'll remember we already found absolute uncertainty. So for example, zero point 0.4 divided by 1.78, and will, and you'll remember I had it as this, so zero point 0.4 divided by 1.78. And then we round percentages to just one sig fig. So that actually just rounds, I got 0.22. That's going to round down to 20%. So I did that for each of the, excuse me, the mean volumes of NaOH. So they got pretty small down here, 5% and 2%. That was from the 0.15 divided by 2.86 and zero point 0.1 divided by 4.26, just taking the absolute uncertainties of the volumes and dividing them by the measurements. All right, the concentration of NaOH, I was told it was plus or minus 0.1. Again, in your report, you would need to include how you found that plus or minus 0.1. That's the one piece I'm not showing you here. And so that's just going to be the same for all of the NaOH. Then the volume of HCl was 25.00, and the graduated cylinder or whatever you use to measure. It could have been a pipette or graduated cylinder, volumetric flask, any of those things. But you reported that the uncertainty was plus or minus 0.05. So that will be the same for all of your trials, because your volume of HCl was the same for all of your trials. So I find those three percentages. And then in order to find the uncertainty, the relative uncertainty for that calculated concentration, again, I'm using the square root of the sum of the squares methods. There is another method where you just add these percent uncertainties, but if you use the square root method before, you should continue using it here. So any measurements that went into my calculation, which are these three in this case, I need to include their uncertainties here. So I take this uncertainty and then I round. Again, percentages we generally report with just one significant figure. So this actually just rounds down to 20%. And that's for the first trial, but I did that for all of the trials. So that's how I got these values here in this third column. And you can even be really, really clear. Something like column 3 in table 5, just to make sure that everything is just really, really, really clear. These were, this is, oh, actually, this would be table 5, sorry, column 2. So just make sure that things are labeled really, really clearly. Okay. So now, my last step, I have a whole list of percent uncertainties for each of the values I calculated. You wouldn't actually report that in a final, sorry, okay, I guess we're stuck with these annotations. You wouldn't actually report that. Oh, here we go. Okay. There we go. Okay. So you wouldn't actually report these percentages, excuse me, in your final report. You would then use these percentages, go back to your calculations, and find an uncertainty of your calculated HCl. So, for example, my 25% or my 25 degrees Celsius, if I know the uncertainty is 8%, I just take 8% of what I calculated and I get an absolute uncertainty. So the last step is to go back to absolute uncertainties using the relative uncertainties you just found that propagated the error from all of the values that went into your calculation. So percent uncertainty that you just found, those are these times the calculated HCLs times what you just found in your calculations. And now I have a whole list of uncertainties, and I can use these. I'll report these, and I'll also use these as the values in my error bars. All right, thanks for watching.